Parts of the electromagnetic spectrum. So it says fill in the gaps using the drop-down menu. The diagram shows the names of some parts of the electromagnetic spectrum. Okay, remember, so we've got radio waves at one end. They're the large wavelength, low frequency waves, and then all the way at the other end of the spectrum is the high frequency short wavelength waves, which are called gamma rays. The radio waves have the lowest energy, moving through to the high energy gamma rays. And the part of the spectrum that we could see is named the visible light spectrum. That's also broken up into the different colours. And then the energy that the waves have start off at lower energy at the radio waves, and they head up to the higher energy at the gamma rays. So let's answer the questions then. It says the three types of radiation are labelled with letters. P is called, so here, after radio waves, you get microwaves. So microwaves. The radiation type Q is used for, so this is actually infrared radiation, infrared just before the red part, the colour spectrum. And infrared, it can be useful for, well, it's a thermal radiation, so heating. You can also use it for shortwave communication, like with your remote controls, so you can turn the TV on and off using infrared radiation. And so let's see what the lists are. So you're not going to detect broken bones, that's X-rays. Sun tanning is UV. Detecting forged banknotes, UV. So it's making toast. Basically your toaster glows, the wires get hot and glow red because that's the thermal infrared radiation coming out and toasting your bread. The radiation type R is more dangerous than radio waves because, right, okay, so R is more dangerous than radio waves. R's higher energy radiation, and so that higher energy radiation can damage cells. So let's see what their options are. High speed, no, they all travel at the same speed for a given medium. Has a longer wavelength, that's incorrect. The wavelength decreases that way. Okay, so this is actually shorter wavelength than radio waves. It does have a higher frequency, which is linked to the energy, so it's higher energy because it's high frequency, and the amplitude's not. That's to do with how intense the light is. Right, so higher frequency. Okay. That's this one. Well done, infrared comes from very hot objects. True. Next set of questions. Radiation and visible light. Question 1. Some thermometers work by detecting the radiation emitted by warm human bodies. What type of radiation is this? Okay, so thermometers are detecting warmth from the body, and the radiation type is infrared, like the toast or toaster. Question 2. Not that that's the correct answer, I'm just clicking to stop it moving. Which colour in the visible light spectrum lies between green and indigo? Okay, so the colour order, the bands, the 7 main bands are red, orange, yellow, green, blue, indigo, violet. You can remember this by just simply put Roy G. Biv, that's the first letter for each of the words. Or you could turn it into a mnemonic, Richard of York gave battle in vain. Okay, so we're looking for we've got the gave bit and we've got the in vain bit, so gave battle in vain, it's blue. And then question 3, which of the following is true about electromagnetic waves? Okay, they are transverse, that is correct. Okay, electromagnetic waves are transverse waves. That means that the direction of the wave is perpendicular to the whatever's causing the wave. And then what's this one? Let's rubbish these ones. They cannot travel through a vacuum. Totally incorrect. How would we receive light and heat from the sun if the electromagnetic waves from the sun couldn't travel through a vacuum? They're certainly not longitudinal. That's where the direction of the waves is parallel to the oscillation, and that's for sound. Sound waves are a good example of longitudinal waves, compression waves. They're always visible. Incorrect. There is a visible spectrum, okay, but there are also parts that we cannot see. For instance, radio waves, X-rays, gamma rays. So I'm putting they are transverse. And then question 4. Which of the following is false about electromagnetic waves? They travel at different speeds. Well, they all travel at the same speed for a given medium. Okay, so they can travel at different speeds, but they would all travel at that speed within that medium. They are sometimes visible. That is correct. There is a visible part of the spectrum. They are transverse. That is correct. Oh, sorry, this is saying what's false. Okay, so that's correct. That's correct. They have different wavelengths. That is correct. Okay, they all have different wavelengths depending on what part of the spectrum. So the false one is they travel at different speeds. Okay, they all travel at the same speed, but their speed can change if they enter a denser or less dense medium. Optically dense or less dense medium. What is the speed of an electromagnetic wave in a vacuum? Okay, so the speed of light in a vacuum, this is the maximum speed light can travel at, is 300 million meters per second. Now this times 10 to the 8, okay, that's the correct size. 1, 2, 3, 4, 5, 6, 7, 8 zeros. So if that said 3 times 10 to the 8 meters per second, that would be correct. It's just it would be in a standard notation, okay? The number times by however many powers of 10, so how many times you need to multiply by 10 to get to the correct number. So just to reiterate, 3 times 10 to the 8 or 300 million meters per second, that's the answer. Right, check answers. All correct. Some information here is this one. Electromagnetic waves all travel at the same speed. The longer their wavelength, the shorter their frequency. And then this one says electromagnetic waves do travel at 300 million meters per second. Electromagnetic waves. Complete the text about electromagnetic waves by dragging the tiles into the correct place. Okay, so we've got these options. Okay, we can scroll through them. So let's read the sentence. Light is a type of, I'm guessing electromagnetic wave. Electromagnetic wave. Our eyes can detect a certain, is that frequency? Let's see, is frequency there? Our eyes can detect a certain frequency range, and that range is the visible part of the spectrum, and we refer to this as visible light, I'm guessing. Visible light. All electromagnetic waves are something waves. So what type of waves? They're not longitudinal, they are transverse. This means that the electromagnetic vibrations are at right angles to the direction in which the energy is being transferred by the wave. So right angles perpendicular. All electromagnetic waves travel at the same speed in a, I wonder if it's a vacuum. Let's see. So all electromagnetic waves travel at the same speed in a vacuum. And they all transfer energy from a source to an observer. Birds can detect electromagnetic waves with higher frequencies than those that humans can see. Electromagnetic waves with frequency higher than visible light are called, so the next one's up, there would be ultraviolet. And then electromagnetic waves with frequencies lower than visible light, so that's the infrareds just below the red part of the spectrum. All objects emit energy by infrared radiation, and the object, the more energy it emits. So the hotter the object, the more infrared it emits. And then finally, I'm guessing electromagnetic waves with high frequencies have low wavelengths, and the different types of radiation are grouped according to the wavelength and frequency. They form a continuous spectrum. Okay. Using electromagnetic radiation. The waves in each part of the electromagnetic spectrum have different uses. Fill in the parts of the spectrum for each use using the drop-down menu. So we've got some statements here linked to the letters A to G, and then from the drop-down menu we're going to select what part of the spectrum that statement belongs to. So the first one says, observing the internal structure of objects, airport security scanners and medical diagnosis. Okay, so we will use the X-ray part of the spectrum to see into luggage at an airport, to get X-rays, okay, to see the internal structures of objects. Then it says for B, vision, photography and illumination. Okay, well that's visible light. We use the visible light part of the spectrum for illuminating objects, for photography, for our vision. Next part of the spectrum says broadcasting, communication and satellite transmission. Okay. Now, interestingly, we use radio waves and we use part of the microwave spectrum. But it doesn't mention anything about cooking our food, which microwaves do in a microwave. So I think this is then the radio wave part of the spectrum. Security marking, fluorescent lamps, detecting forged banknotes and disinfecting water. That is all part of the uses of ultraviolet light. There it is. E, cooking, communication and satellite transmission. Okay, so with the cooking part of it, then I'm going to select microwaves because we do communicate with microwaves. Sterilising food and medical equipment and the detection of cancer and its treatments. Okay, so when you're sterilising food and medical equipment, you need the highest energy rays to kill off any bugs and germs, and that's gamma rays. And then finally G says cooking, thermal imaging, short range communication, optical fibres, TV remotes and security systems. So our TV remote is infrared, optical fibres, you can send infrared signals down, thermal imaging, heat, okay, cooking, like cooking your toast using a toaster, that's all infrared. Alright. Uses of electromagnetic waves. Complete the sentences about the uses of electromagnetic waves by selecting the correct options from the drop-down menu. So something, the part of the electromagnetic spectrum that our eyes detect. So something, the visible light is the part of the spectrum that our eyes detect. Cameras can also detect. Infrared radiation can be used for communication. Short ranges, okay, so you're going to be able to like switch over the channel using your remote control from within your living room, but you're not going to be able to maybe send that signal from one end of the street to the other. Or certainly not further than that. Such as between computers in the same room, a TV remote unit and a TV, and along optical fibres. Something uses the communication and satellite transmission. So use for communication and satellite transmission. Oh, hang on, let's just read. So it's either going to be radio waves, or it potentially could be microwaves. It's going to talk about cooking food as well. So let's see. So used for communication, satellite transmission, including mobile phone signals, transferring energy for art. Right, okay, so it's transferring energy to food as well. That's microwaves. Radio waves are used for communication, including between controllers on the ground and space, and have. So we're talking about the wavelength. Now you know the spectrum starts there with the radio wave, which is the longest wavelength part of the spectrum. And then it goes to microwaves, which are shorter wavelengths. So that means that the radio waves are longer than the microwaves. Ultraviolet radiation transfers. So we've got less energy than visible, or more energy, or the same. So visible light is a certain frequency. A higher frequency is beyond the violet part of the spectrum, which is the ultraviolet part that has more energy. And what have we got? The energy can be used to disinfect water by killing living organisms in it. Some materials absorb this radiation and re-emit it as visible light. These fluorescent materials are often used in security markings. They're only visible under this type of light. X-rays have something than ultraviolet rays. So what is it that they have? Okay, so we're talking about wavelength. The wavelength should get shorter the higher the frequency. And X-rays are more higher frequency than ultraviolet, so their wavelengths are shorter than ultraviolet. These rays can be used to examine the inside of metal objects and luggage and security scanners. And then gamma rays finally, what's it asking for? Transfer this special kind of energy, transfer a lot of energy, transfer a small amount. A lot of energy, okay? The most energy is transferred by gamma rays. They're the high energy part of the spectrum. They can kill cells. For this reason, they are used to sterilise food and surgical equipment or instruments, and to kill cancer cells in radiotherapy. They can also be used to detect cancer. A chemical that emits the rays is injected into the blood. The chemical is designed to collect inside cancer cells, and a scanner then locates the cancer by finding the source of the rays. These rays can pass through all the tissues in the body. So to check the answers. Astronomy. Okay, so look at the image. So this is a graph. So it's there's the spectrum, and so it's telling you the wavelength of the spectrum, going from the very short wavelength, the gamma rays, all the way up to the large wavelengths, the radio waves. And then this on the y-axis is saying the percentage of that part of the spectrum that's absorbed by the atmosphere. Okay, and bearing in mind gamma rays and ultraviolet, okay, that coming from the sun, we do not want to be bombarded by gamma rays, okay, and you can see that the atmosphere actually absorbs all of them 100%, and then part of the lower energy UV light spectrum starts to not get as absorbed as much. Okay, so we actually receive some ultraviolet light, and then it drops right down to suggest that most of the visible part of the spectrum get through, and then varying parts of the infrared, so we feel some heat from the sun. We can see all the colours, and that colour comes from the sun's light, so reflecting off certain objects, absorbing and emitting, so we see all the different colours of things. But what's interesting from a biological point of view is that potentially maybe eyes were evolved to see this part of the spectrum because more of this part of the spectrum gets through the atmosphere. Anyway, back to the physics. So then it comes back up to a lot of the microwave and high energy infrared doesn't get through. Likewise, the larger wavelengths from radio waves don't get through. But then a lot of the radio waves and quite a bit of the microwaves get through, hence why potentially it's good using that for transferring energy in communication, because it wouldn't be good if it got absorbed by the atmosphere, because you wouldn't be able to send communication signals through the atmosphere with radio waves and microwaves like we do. Right, let's get to the question. Okay, type the correct answer into the text. So we have to type the answer. Something at all wavelengths of the electromagnetic spectrum is emitted by stars and other space objects. Okay, so that's light. So light at all wavelengths of the electromagnetic spectrum is emitted by stars and other space objects. Something are used to study this radiation. Telescopes. Telescopes are used to study this radiation. Different something require the use of different kinds of telescopes, so the different wavelengths require the use of different kinds of telescopes. Something waves are affected differently by different materials. This depends on the wavelength. So electromagnetic waves are affected differently by different materials. This depends on the wavelength. For example, the diagram on the right shows which wavelength can pass through the atmosphere and which are absorbed. Most telescopes use curved mirrors to focus the electromagnetic radiation onto a central sensor. The something of the radiation being studied will determine the type of material used for the mirror and the size of the telescope. Well, we've already said that it's the wavelength means that we require different telescopes, so it's the wavelength of the radiation being studied will determine the type of telescope. All electromagnetic waves can travel in a vacuum, but the something absorbs some of them. So the atmosphere absorbs some of them. Telescopes in something are used to study any frequencies that are not absorbed by the atmosphere. Okay, so in space. So the Hubble telescope's in space, and that's used to study any frequencies that are absorbed by the atmosphere, because it doesn't matter, there's no atmosphere in space. Okay, let's see, check the answers. Correct. Dangers of radiation. Match the statements on the right with those on the left. So we've got gamma rays, infrared radiation, ultraviolet radiation, and then the statements are cell mutations deep in the body that may kill cells or cause cancer, damage or destroyed cells causing rapid skin burns, and skin cancer in long term. So we've kind of like got the most dangerous rays are going to be for this one, and then this is less damaging to the body, less dangerous, and then finally, it's all damaging, but this takes a long time, long-term skin cancer. That could be from, oh, this is the least, isn't it? Because it's just damage just caused by burning. Okay, so infrared is just a burn. Yeah, so if you receive heat, thermal radiation, you can burn yourself. Ultraviolet, long exposure, could potentially lead to skin cancer if you get suntanned a lot. And then finally, cell mutation and causing cancer, and can kill cancer, gamma rays. Great. EM, that's electromagnetic radiation dangers. Choose the correct answer from the drop-down menu to complete the text about the dangers of electromagnetic waves. All waves transfer energy. Certain microwave frequency can heat water, and this frequency is used in microwave ovens. This heating could be dangerous to people because our bodies are mostly water, and the microwaves could heat cells from the inside. Okay. Mobile phones use different microwave frequencies, and current scientific evidence tells us that in normal use, mobile phone signals are not a significant risk. Okay, normal use, mobile phones aren't a significant risk. If they were, we wouldn't be allowed to use mobile phones. Infrared radiation is used in grills and toasters to cook food. Our skin absorbs infrared, which we feel as heat. Too much infrared radiation can damage or destroy cells, causing it's infrared, so it's causing burns. So let's read that again. It's infrared radiation, so it can be absorbed by our skin. Too much of this infrared radiation can burn the skin. High frequency waves transfer more energy, and so are potentially more dangerous. Sunlight contains, what's the rest of this, because it contains not the null bit but these, so contains gamma radiation, which has high frequency, so carries more energy. Well, it looks like the gamma bit. So high frequency, we were talking about high frequency, which is gamma, so high frequency waves transfer more energy. Sunlight does contain gamma, which is high frequency, so carries more energy than visible radiation. This energy transfers to our cells and can damage their DNA, causing aging, and if the damage is severe, causes I think this is actually just talking about the ultraviolet part, because the gamma rays are going to get absorbed by the atmosphere and they're not going to get through, whereas ultraviolet is higher frequency than visible light. That's correct, and it can also cause aging and skin cancer, okay, in long term. So I'm going with ultraviolet. We can help to protect our skin by staying out of the strongest sunshine and using sunscreen. Right, let's check the answers. There you go. All correct. Next. Okay, so we're going to start with lowest frequencies up to highest frequencies, and it says increasing in danger, and put these in order. So the most dangerous is the highest frequencies, and the least dangerous is the low frequencies. And then we just got to put this in the order of lowest frequency to highest frequency. So we've got microwaves will be lowest, so it goes radio waves, which isn't on this list, then microwaves, then infrared, then it goes visible, which isn't in here, and then it's got ultraviolet, then it would be X-ray followed by gamma. Okay, so that's the order. Check the answers. Correct. Additional information. Yes, microwaves have the lowest frequency and the least hazardous. And yes, gamma and X-rays have the highest frequency and are the most hazardous. Excellent.